Hi, in this tutorial we are going to build a deep learning pipeline that automatically grades the severity of a knee osteoporosis from X-ray images. We'll start by organizing our dataset into training, validation and test dataset and use to visualize to explore the samples. Next, we will pre-process the data and apply image augmentation to make our model more robust. And we will use the ResNet 152 version 2, a very powerful pre-trained model, and fine-tune it for 5 severity classes. After training, we'll evaluate the performance on the test dataset, visualize results with accuracy and loss curves, and even predict random test images. Finally, we will wrap up with a full classification report and confusion matrix and see how well the model is doing. So, let's start with a short demo. We will use the ResNet 152 v2, basically it's a ResNet version 2, and we will adjust it to our needs, and we will build the model and run the training, and after that we will try to run an inference of our saved model using one of the test images, and after that we will run a confusion matrix and we will display the result and examine our model, evaluate our model, how good is it and how can we make it better. So let's jump directly to the installation and the code. So let's start with the installation, and basically we are going to use Python 3.11 and we are going to install TensorFlow 2.17.1, and TensorFlow with a version that above 2.15 requires to run on Linux environment. So basically if you have a GPU card and you would like to use its power, you need to run it on a Linux environment. I have Windows environment with WSL2, so I have a Linux environment and I'm running the whole process in this environment. So what you will see now is our VS Code running on a Linux environment in a PowerShell. So let's cover the installation part. I already done it and created the Conda environment, so let's just cover the commands. So first of all, we are going to create a new Conda environment. I name it TensorFlow 2.17. Basically it's TensorFlow 2.17. Of course you can choose your custom name, and it's run on a Python 3.11. And after that you have to activate this new environment, since now we're going to install several Python libraries. All this process of course running under a PowerShell in your Linux environment. Then you're going to install a TensorFlow. Here you have all the information for installation of TensorFlow in the WSL2 in the Windows environment. If you have a Linux already, of course you can skip it. And then the command is pip install TensorFlow and CUDA equals 2.17.1. If you don't have a GPU card, you can also run it on a CPU environment. It will work perfectly, just a little bit slower. So as I mentioned earlier, we are going to install a TensorFlow, and after that we have to install several Python libraries that are relevant for our tutorial. We are going to install Matplotlib, Pandas, Escape, Learn and Seaborn, and please choose those specific versions. I already checked them and they are working well with TensorFlow 2.17 and with Python 3.11. So this is the installation part, and now you have to download the dataset. I will leave here a link in the installation file. Of course, the whole code and the installation file will be part of the video description. I will leave a link so you can download it and run it on your local machine. And if we copy and go to our browser, you can see this is the dataset from Kaggle. And what really important to understand about this knee X-ray data, that the information is divided to 5 classes. There is class number 0, 1, 2, 3, and 4, and each of those classes has its own images, and basically this is the description for each of those classes. For example, class 0 means a healthy knee image, and class 4 means a severe damage to the knee, large osteoporosis, significant joint narrowing, and severe sclerosis. Basically, I don't understand what does it mean, but if I understand correctly, there are 5 steps of the disease in the knee, and they are presented in those images. Let's go down here. You can see that the dataset here is divided to several subfolders. There is the test, and there is the train, and there is the validation. If we open the test, we can see those 5 categories, and if we click for the 0, you can see here all the healthy images, all the 0 images. Let's close it and let's look for number 4, and here we can see all the knees that are categorized as a 4 category. So basically just download the dataset, copy it to your custom folder in your local machine, and now we are ready to start coding. And basically before that, you can see here I also add the descriptions of the knee categories here, but most important, after you created the Conde environment, don't forget in your VS Code to click Ctrl Shift and P, and then this pop-up will show, and you have to choose Select Interpreter, and here there are all the already installed environment, so you have to look for the one that you just created. I name it in my computer as TensorFlow 217, so I will choose it, and now my VS Code contains the TensorFlow and all the rest relevant Python that I already installed. So now we are ready to start coding. So let's start coding. First of all, let's create a new and fresh Python file. Let's name it step number 1, build the model using ResNet. So let's import some relevant Python libraries. We will import NumPy and Pandas, OS, Random, Matplotlib for plotting and visual our dataset. Let's also import OpenCV and TensorFlow. From TensorFlow Keras application, we will import the ResNet 1.5.2 version 2, which this is our main convolutional neural network, and also the preprocess input that will which prepare our images for the model. We will also import callbacks for training, such as early stopping to stop training when validation loss stops improving. Also reduce plateau to reduce learning dynamically, and model checkpoint to save the best model during the training. We will also import the model class, and that will help us to construct our neural network. Let's also import a dense, dropout, and input layers in order to build our custom classification model. We will use the Adam optimizer, so let's import it as well. And next, let's define the base directory where our dataset is stored, that contains the train, validation, and test folder. Now we will set the training dataset directory, the validation, and the testing dataset directory. The batch size defines how many images we process in one step of training. Let's define it at 16. And the input image size will be 224 by 224. The number of classes is 5, representing our different severity levels of knee osteoporosis. Now let's visualize some sample images from our training dataset, just to do an early check-in and to see some of the images. So we will loop over each class ID from 0 to 4 and randomly select 5 images from each class folder, and after that we will display each selected image in the grid with its class label. So finally we will use the PLT show in order to display all the images in one page. So this is just a sanity check to see that we are loading everything correctly and displaying some random images. Before we run it, I have to fix, I forgot to put here between the two dots the word Keras. I have another syntax error. Of course it should be 5 by 5, not 3 by 3. Let's run it. Great. So now we can see a sample of the result. So here are images for each of the types: 0, 1, 2, and 3. 4, there isn't enough space for class number 4, but we can see that we have all types of the classes. Now let's define a function to pre-process images and labels before feeding them into the model. Let's name it a pre-process. We will send the argument image and a label. First of all, we will resize the image to match the input size expected by ResNet. Then we will apply the ResNet specific pre-processing, including normalization, and then convert the labels into one-hot encoding, which required for categorical classification. Now we load the training dataset using the Keras image dataset from directory utility, and we will do it for the training dataset, the validation dataset, and the test dataset. The parameters are basically similar for those 3 imports. You can see the train directory, the image size, the bed size, shuffling the images. So basically it will be the same step for all 3 datasets. Next, we defined a data augmentation pipeline to increase the diversity of training images. You can see that we are generating more images using a random fleet, some rotation, a little bit zooming, and this will help us to generate more images before the training. Now we begin building the model. First, we define the input layer with the correct image dimensions, and after that we will apply the data augmentation object. We will apply the data augmentation to the inputs, so this is only active during training to avoid overfitting. After that, we apply the pre-processing such as normalization to make the input suitable for ResNet 1.5.2 version 2. And next we will define the ResNet base model. We set include top to false to remove the original classification layer, since we are going to replace it with our requirements. Next we will freeze the base model weights so that pre-trained features are not overwritten during the training. So we would like to keep the original weights. After that, we will add a dense layer with 128 units and a ReLU activation as a custom classifier head. Then we will add a dropout with a rate of 20% reduced overfitting. And next we will define the final output layer with softmax activation to predict probabilities for our 5 classes. Now we will build the complete model by combining inputs and outputs. And the rest is now we will compile the model with the Adam optimizer with a very low learning rate, categorical cross-entropy loss, and accuracy as a metric. Now let's define a callback to reduce the learning rate during the validation process. And after that, let's define early stopping to halt training if validation loss doesn't improve for 25 epochs. And let's define the model checkpoint to save the best model based on the validation loss. So each time the model got a better result, we will save our best model in this file. Now it's the training part. Let's train the model on the training dataset with the validation monitoring and the defined callbacks. So all the arguments will be sent to the training. Please notice that we are running 500 epochs. Basically, we will stop earlier. So the 500 epochs is a final or a high value. After the training, let's evaluate the trained model on the test dataset to see its final performance. And after that, let's extract training and validation accuracy and loss values from the training history and display it. Do a brief overview. I can see I have here a syntax error. This is not the right argument. It should be shuffle. So let's fix it here and here and here. Great, that's it. Let's run it. So first of all, we will see those sample images. Those are the images, the same as our first step. It's random images for each of those classes. We can close it. And now we are loading the dataset. You can see here, found more than 5,000 images. Next, we are loading them. What is the validation images? More than 800. And next, we are loading the test dataset. More than 1,600 images for test images. And now we are waiting that the training will start. Let's wait a few more seconds and we will see the pace and the progress of the training. So now we can see the progress of the first epoch, and this is the accuracy. Those warning messages, you don't have to worry about them, just warning. And basically I think I will stop the recording now. Of course, we are not going to wait 500 epochs. The early stopping process will terminate it before the last 500 epoch. I don't know yet how many epochs it will take to train all the images, but let's stop the recording and I will resume it in the end of the training. So the training has finished and let's see the results. So those are warning messages, we can skip them, and here it is. First of all, we can see that we trained 64 epochs out of the 500, so there was an early stopping. And also we can see here the accuracy, and also we can see the loss. So this is the right line. So this is the accuracy for the training, the loss for the training, and this is the value for the validation accuracy and the validation loss. So the training is finished, and I believe that now we are ready to start running some inference on the results, and we can test it on several test images. Now it's time to test our model. We will do it on 2 steps. The first one will be on one single and random image. Let's create a new Python file. Let's name it step number 2, test our model. And we will start with importing some Python relevant libraries. And basically it will be the same. Please notice that we will use sklearn. We will import classification, report, and confusion matrix to evaluate our model. We will also use a Seaborn to create a beautiful visualization of our confusion matrix. So let's define the test dataset path from images for evaluation where we stored it. And next we will define the model path where the trained best model was saved. Let's set the input image size, the same size, 224 by 224. Let's extract the class name from the test folder by listing its subdirectories, and let's print them. And after that, let's load the trained model from the disk using TensorFlow, and let's confirm that the model was loaded successfully by printing its summary. Now let's define a function to test the model on a random image from the test set. So basically let's randomly select a class folder. We grabbing a random choice out of the class names, and then we will get the full path for our class folder. And after that, after we retrieve a random class folder, we need to extract a name of basically to pick an image file from this class folder. So we'll use the random and choice, and out of the list of all the images inside the random folder. And let's get the path, the full path of this image. After that, let's print the path so we can see the name of the file, and after that we can load the image using OpenCV. And let's convert the image from BGR to RGB since OpenCV loads it in BGR mode. Now let's resize the image to match the model input size. And just for debugging, let's print the size of the image before the preprocessing and after the preprocessing. So it should be the resized image. Now we will expand dimensions to add batch size of 1 to our image and run the preprocess. Basically we are creating a batch of images that contain only one image. And once again, let's print the shape just for debugging. Now let's make the predictions using our model. So first of all, we will grab the prediction class index, the one with the higher predictions value, using the argmax. And after that, let's get the predicted class names using our class names variable. And once again, only for debugging, let's print the information about the prediction. Great. So after that, it's the display part. We will use the pyplot library in order to display the image along with the predicted class. So let's create a figure. Let's create a figure of 6 by 6, and then we will add the predicted class name into the title of this image. And finally, let's display the result. So we will display the true value and the predicted value next to each other. Great. And of course, don't forget to activate our function. I have a syntax error here. I forgot to load the class name, so it should be sorted and test path. Okay. So let's run the code. The steps will be loading our saved model, the one that we just trained. Then we will load the test folder. Basically, we are going to choose a random folder name out of those 6 folders, and after that we will choose a random image and we will try to predict the image. So let's see the result. Great. As you can see, it took a random image from class number 3, and the true value is 3 and the predicted value is 3 as well. Great. Now let's run a prediction for all the test images and create a confusion matrix, so we can display all the true labels and all the predicted labels in one diagram. So in order to do that, let's define a function to evaluate the model on the entire dataset, entire test set. So we'll create lists to store true and predicted labels, and we will loop through each class folder and its images. And so as you can see, we are doing basically the same process on our one random image. For each image path, we will load the image using OpenCV, convert it to RGB, resize the image, pre-process the image for our model, and after that we will run the prediction, grab the highest score, and grab the index, the class index between 0 and 4, and after that we will add each class index and predicted class index into these 2 lists. And when the loop is finished, we are ready to generate the confusion matrix based on these 2 lists, and we will plot the confusion matrix using Seaborn. So one axis, the x-axis will be the predicted label and the y-axis will be the true label. So these are all the parameters needed for displaying the results. Let's also create a classification report and we can print it, but basically we done and we can run the code. So let's run it and see the result. We of course will skip the first phase, which is prediction of a one random image. So this is the predicted random image, a great prediction. Let's continue now for the evaluation of the all images in the test folder. So you can see here in the log in runtime the process for each of the images. Let's wait a few more seconds until it covers the whole folder. So here is the result, the confusion matrix of all the test images. It took about 2 or 3 minutes since it covered more than 1000 images in the test folder. So first of all, we have here the predicted label axis and here the true labels. Anytime that the true labels match the predicted label, that means that the model is a great model. Let's, for example, take the category named 0, and this is the second category named 0, so this is the true label of 0 and this is the predicted label of 0. You can see that if we are looking for the true labels, we can see that most of the values are sitting here. You also can see the color. So the model predicts very well the class 0. And if, for example, we will take the value 1, the category 1, and if the most of the values were here, that means that that means that the model predicts also well the class number 1. But we can see that the model predict most of the true values of class 1, which is 172, as class 0. So basically, if all the values were here on this line, this is our best model. We can see that, for example, for class 2, most of them are here, so the blue color is more dark from class number 1. So our model is not perfect. It may classify great images from class 0 and class 2, but in order that our model will generate better results, we mostly need to feed the model more images from class 1, I believe class 1, and also class 4. Although class 4, if I'm looking here, I can see that most of the values are here in this line, so there are 8 misses here and 8 misses here, but most of the values of class 4, maybe we have less images in the test folder. But basically, if we will feed the model more images in class 1, we will probably get more accurate model with these categories. So that concludes our tutorial. You are most welcome to subscribe my channel. Bye bye.